skip my introduction because he's motivated the whole talk. And what I'll really be talking about is then just the atomic physics, the collision physics of three-body recombination. You've heard it called three-body association and maybe a couple of other terms. But the term that I'll use is three-body recombination. This work, the newer stuff that I'll be talking about was done by my postdocs and I'll be showing some older results as well. I should mention that we were sitting here almost 3 years ago at another ITAMP workshop on the early universe when it was told to me that this reaction might be important, the three hydrogen collision and recombining reaction. And so we in fact started looking at developing the tools to be able to try to handle these systems. So it's nice to come back and see that effort will be useful since it still seems important. In any case, just to be clear, three-body recombination is the collision of three free atoms colliding to make a bound molecule in some rho vibrational state, giving up the binding energy to the relative kinetic energy of the fragments. Now, of course, if you have three different ones, I've only indicated one of the possible final channels that one would typically have. And of course, the examples that we've heard about, especially in the last talk, three hydrogens colliding to form H2. One can also think about this as a three-body recombination, H2 plus two H's forming another H2. And then finally, this helium, which can largely be neglected, but whose abundance can largely be neglected, is also listed there. And of course, I've just taken these from, of course, Simon and Daniel's review on the evolution of these early clouds. Okay. If you just turn the time arrow around, you get collision-induced dissociation, right? So everything is exactly the same. I just turned the arrows around. And the other possible inelastic process with these three particles is if you already have this molecule in some vibrational state, it can collide with one of the free atoms and change the rho vibrational state. It could be relaxation, could be excitation, but this is also another possible inelastic process. Of course, I didn't show it, but there's also the exchange reaction, what's often called reactive scattering, where the B and the C, for instance, exchange. So to give you a sense of the complexity of this problem, now I'm doing theory, I should be clear, I'm doing calculations, to give you a sense of the theoretical complexity of the problem and why these calculations don't already exist. I'll just step you through some of the pieces here. So we need to solve the three-body Schrodinger equation to calculate these rates, which of course is a 9-dimensional problem since it depends on three particles' coordinates. You can go to the center of mass and get rid of 3 dimensions. You can use the total orbital angular momentum representation and get rid of a few more, but you still end up with coupled 3D equations. Okay? If we use another approach that I like, that's especially suited to this three-body recombination problem, then which is called the adiabatic hyperspherical representation, then you can reduce this to coupled 2D and coupled 1D equations. So you do it in 2 steps. I don't want to go through the details, but I want to give you a sense of the kind of calculations that are needed here. So the main computational task in the end to solve finally, to get to this last bullet, is that we have to solve J complex coupled 2-dimensional partial differential equations. The equivalent of the original Schrodinger equation is exactly that. If we have total angular momentum J, then there are J 2D partial differential equations to solve, which ends up being, once you choose your numerical method, a main job of diagonalizing a sparse generalized eigenvalue problem of order 10 to the 4 times J. Okay, so it's a fairly substantial computational problem, but these days can be done fairly straightforwardly on workstations if you're willing to wait a week or 2. Okay, so, but we do this. Now, once you've solved those problems, you of course have to get a get the observable, something to compare to the experiment, something that can be used then in the simulations for the evolution. The first thing that you get from this by solving all this is a scattering amplitude that depends on initial momenta and final momenta. But then you have to, of course, do all the integrating over the final momentum and averaging over the initial momentum, Maxwell-Boltzmann initial distribution of momenta. And this breaks the theorist's heart to do all this averaging after you've worked so hard to get all this detailed information. But, well, I guess that's what has to be done. Just to give you an idea of what the three-body thermal averaging looks like, this is the result, at least in the zero energy limit. This actually has to be revisited for not the zero energy limit. And zero energy limit, I mean probably less than pico EV collisions, okay, which is micro-Kelvin sorts of temperatures. That's where I'm coming from. I'm one of those guys who skipped over this astrophysically relevant regime that Daniel's talking about to go to the ultracold. So I'm coming from ultracold, where we routinely talk about micro-Kelvin and nano-Kelvin. So this is the answer in the zero energy limit. There's actually some fundamental derivations that have to be done about three-body scattering, because, again, three-body scattering in the quantum regime isn't something that's been tackled all that much in the literature, nuclear physics or atomic physics. So even some of these basic equations have to be checked. Whoops, there we go. But just to give you proof that we can actually solve it despite all these challenges, here is a calculation that we did in the ultracold regime. So just to give you a sense of what I mean by ultracold, I've listed the temperatures by some of these things. So this is about 7 times 10 to the minus 4 nanokelvin. Okay, then that's actually too ultra for even the ultracold people. That's just what we had. So we were just making a different point. I just wanted to show it for a example. Okay, so these curves actually come in pairs. So the red and the green go together. These are the recombination rates, so I should say that. I'm plotting the recombination rate as a function of the scattering length. You can think of the scattering length as the depth of a two-body potential. So this calculation is actually for sort of fake cesium atoms, okay, with some model for their interaction. It's not the real interaction. We've taken some model two-body potential that actually only has, in this case, 2 bound states, and you adjust the depth. Why do we do that? Because the ultracold people care about this parameter. But for our purposes, let's just think about it as the depth of the potential. And the depth of the potential increases as we go that way. So we start with 2 bound states. The red one is the deeply bound state, and the green one is the weakly bound state. So this is one calculation. This is one temperature. This is another temperature and another one. So that's 10 to the minus 4 nanokelvin, 10 to the minus 3, 10 to the minus 2. This corresponds to 10 to the minus 1. And so this one is all the way up to 7 nanokelvin, this one down here. So we're getting close to astrophysics, right? So one thing I also wanted to point out from this picture is that even with the challenge of the computation, we're calculating things over 4 orders of magnitude here, and actually from 10 to the minus 30 to 10 to the minus 12-ish in the rate itself. So we're doing a fairly decent job with this calculation, covering orders of magnitude in the rate. So we have some room and we have some technology to bring back to this astrophysical problem. Why do the people in ultracold care about three-body recombination? Well, for much the same reason that we've been talking about here, is that when the density gets high, three-body recombination takes off. And what they want, I mean, when I talk about ultracold physics, what I mean is people who take and trap atoms in essentially a harmonic oscillator that's built by putting magnetic fields together. They trap these atoms in this trap, cool it down to ultracold temperatures. In this case, in this example that I borrowed from Randy Hewlett, they cool it down to 800 nanokelvin, 500 nanokelvin, 240 nanokelvin. Okay, and why do they want to do that? They want to look at quantum degenerate gases. They want to look at the quantum statistics of these degenerate gases. Okay, and I like this picture because it shows the difference between bosons and fermions when you cool it down. So of course the bosons condense and the fermions just go down until you have everything below the Fermi level in all the lowest states, and so it stays much larger for a comparable number of atoms. But as you do this, the system, of course, gets denser, and where it gets dense, three-body recombination takes off, and they lose their lovely atoms that they've worked so hard to trap and cool to making molecules. And the molecular binding energy is so large that it kicks the molecules and the atoms out of their trap. And so what they start seeing is this cloud just shrinks and goes away. So they really don't like three-body recombination. They want to avoid it. And so that's the context I'm coming from, is that we were calculating this to help the experimentalists figure out how to avoid this, okay? Or at least understand it better so they can optimize their experiments better. Now, I think this is a particularly appropriate picture for this crowd too, because it's actually shown up on an astronomy picture of the day twice. So I always like that the astronomers pick this up. They like it because it showed up there because it's a nice example of Fermi pressure. So, but what can we learn for the question we're addressing now from these calculations at ultra-cold temperatures? Well, I think there's a couple things we can take away, but let's focus on the set of curves that I've circled there, okay? These are the calculations done at the highest temperature, still nowhere near really relevant, but what I want to point out here is that for this case, this is the energy level diagram for the atom that or for the molecule that you produce. So you have a weakly bound S wave and a deeply bound S wave, and the weakly bound state is much larger. Okay, these are the vibrational states. So the recombination into the weakly bound state by far dominates. Over here, we have a set of 3 curves with this sort of energy level diagram. These are the row vibrational energies of the molecule produced. S wave, you still have the 2, deeply and weakly bound S wave, but you have an even more weakly bound D wave. Okay, and the most weakly bound state has the highest recombination rate by far. Now, I should point out that these potentials, these model potentials we used, actually had a very soft core, a very unphysical soft core, that when we've done some calculations with a more realistic hardcore potential, like you would have in a typical Born-Oppenheimer atom-atom potential, the differential gets even bigger. The weakly bound state dominates in the recombination by, a much larger fraction, by a much larger factor. And the importance there is that if you have three-body recombination making H2, you're most likely making it in weakly bound states. And it gets to lower states by subsequent collisions or other processes. Okay? Now, we haven't done just ultra-cold. We've also actually done cold recombination. We've even done cold recombination for light atoms with realistic potentials. So, for example, we've done helium plus helium plus helium makes a helium dimer plus a helium. Now, maybe some of you didn't even realize that there was such a thing as a helium dimer. It's actually bound by 1.3 millikelvin. So again, probably not so relevant, but look, we went all the way up to 100 millikelvin here. We're doing really well, right? We've gone up by orders of magnitude. So give us 6 months, we'll be doing the right calculations. But this does illustrate a number of things. So the ultra-cold regime is really over here where this guy, so what, I should back up a second. I'm showing the recombination rate is a function of collision energy. And what I'm showing is actually all the different contributions of the different partial waves for the three-body system. So you may recall from two-body scattering that when you do quantum mechanical scattering calculations, you decompose it in partial waves, and then you can add them up one by one. And at low temperatures, you only need S wave, and as you increase the temperature, you have to add higher and higher partial waves. This is exactly the same, and this picture is just showing how these different partial waves contribute. So the black line is the total, the red line is the S wave, J equals 0, except the difference is when you do three-body, especially when you have 3 identical bosons and identical particle symmetry comes in, they don't come in a regular pattern. So it's 0, 2, 3, 1, 4, 5, 6, okay? And it even depends on which energy you're at as to what order they come in. So you have to do a bunch of J's, and this is going to be one of the challenges that will come up then for doing astrophysically relevant calculations, to orders of magnitude higher temperatures, is doing all of these J's. Okay? Now notice how big is that rate constant? It's 10 to the minus 27. Okay? Now the range that Daniel mentioned for the H3, the H plus H recombination, was down around 10 to the minus 30 to 10 to the minus 33. I can tell you, at least from the experience I had in the ultra-cold regime, 10 to the minus 30 to 10 to the minus 33 is quite a small recombination rate. Okay? This sort of range, but it's not out of the range of what's reasonable. So that could possibly be true, but it will be interesting to see because, again, a lot of these systems actually have much larger rates. And you can see that out here at the top end, it does look as though they're starting to fall off. So it might be that by the time you go out here, a couple more orders of magnitude, it has fallen off by quite a bit more. We've done other systems, and you have to look closely probably to see the difference between these, but there's a 3 and there's a 4. Okay, so this is an isotopic change. Helium-3, helium-4 doesn't form a two-body bound state. So the only possible final channel in this calculation is still the helium-4 dimer, but the change is actually quite dramatic. Okay, so this isotope effect is actually quite huge in this case. So the rate here is an order of magnitude larger at the low end, and you can see many fewer partial waves contribute. Okay, so it means that you may not be able to estimate very well what you need. You may just have to do the calculation. Well, we've done some other things on other light atoms, and again, this looks kind of interesting, forming lithium hydride, except this is lithium hydride in the triplet state. So again, it's probably not so relevant, and you may not have even realized lithium hydride in the triplet state was bound, and I should have given the reference, but that's from a paper by Robin Cote and a few others from here at ITAMP, giving the potential in these bound states. But the lithium-7 hydride triplet is bound by 40 millikelvin. Okay? You might have noticed a theme here. So far, we're only handling systems with one weakly bound state. And again, it's for technical reasons, which I'll get to in a second. But again, fairly high rates, and the contribution of the different partial waves is following a sort of similar pattern. Then finally, helium plus lithium. Again, another system you may not have realized is bound. It's bound by 5 millikelvin in this case. And but this system is a little bit different than the others. It has two different possible final channels. One is making the helium dimer, one's making the helium lithium molecule. And again, you can see the difference in the rates to those two possible final products. Again, fairly large rates, and the contribution up to 10 millikelvin in this case, coming in a fairly different way. And in this case, we even lose the property that the most weakly bound state dominates in the recombination, because the helium dimer here is the most weakly bound state, and that's this picture where the rate is 10 to the minus, a couple times 10 to the minus 28, where up here it's, 4 or 5 times 10 to the minus 28. So we even lose that property. So it looks like it might be that we just have to do the calculation to find out what the answer is. Imagine that. Why did we pick these systems? Well, the answer is because they're simple. And all we can handle right now is simple. And they're simple, particularly when you look at them like this. So I told you we use this adiabatic hyperspherical approach. Well, one advantage of it is that we reduce this three-body system to a set of adiabatic potentials. Now, I'm not going to go through the details of how we get these, but you should think of these potentials. These are potentials for the three-body dynamics. The hyperradius is just the overall size of the three bodies put together. And you can think of these exactly like Born-Oppenheimer potentials. Okay? And so when we do three-body recombination, we have to start on these potentials up here that I've labeled lambda. And there's actually an infinity of these. I've just cut them off here. These go to 3 free atoms. Excuse me. So that's our initial state. You come in with 3 free atoms. There's coupling in here. And then you go out on one of these molecular channels. Okay? And in this case, like I said, You can make a helium dimer, or you can make the helium lithium molecule. So in this case, there's only 2 of these, and only a handful of those that we have to worry about. What about a more realistic system that would be astrophysically relevant? Well, so I'll look at helium plus hydrogen plus hydrogen. Again, this is the one we're actually working on right now to calculate the 3-body recombination rate, and again, over really this astrophysically relevant temperature regime. And we chose this one rather than 3 hydrogens because it's simpler. Okay? We can only make H2 in the final state. There's no helium H bound states. Okay? So the problem is that where I've treated 1 or 2 molecular states before, H2 now has more than 100 row vibrational states possible in the end. Are they all important? We don't know yet. But unless we do technical development with the method, we have to include every one of those silly 100+ row vibrational states. So we're doing technical development. And what I'm showing here are the lowest 100 or so potentials of those same adiabatic hyperspherical potentials for the 3-body system. I'm showing only the ones that go to the S-wave molecules. Okay? Then I can add the D wave. Of course, by symmetry, we only get even partial waves or odd partial waves. So add the D wave, add the L equal 4, and I could keep going up to L equals 30 or 40 or whatever, however many angular momenta are actually bound here. But I think you start to get the picture of how much more complicated these potentials are going to be. Because what I have to do scattering now is solve the radial equations on all of these coupled channels together to extract S matrices. Okay? So scattering matrices. But I think we can do it, or else I wouldn't be up here talking to you about it. It's just going to be more complicated. But we've got bigger computers, so we can handle that. Just to give you a little bit better sense, though, about the 3-body recombination part, what I showed you before, 3-body recombination, remember, and by the way, I didn't put it on here. This vertical scale is the potential energy, or just the energy in Kelvin. Okay, just to give you a sense of how big these things are. 3-body recombination starts up here at 0 energy. That's the 3 free particles. The particles are going to come in here, go into the region where they're coupled, then come back out on one of these molecular channels. And if I blow up the region around 0, over sort of the range of collision energies, because astrophysically you probably want up to a few thousand Kelvin, so that would be collision energies, along here. We're going to come in, and you can see how much denser those curves start getting up there. So this is going to be a problem. How many of those curves do we actually need? Well, if we just make an estimate at 3,000 Kelvin, I'm showing now only the L equals 0 curves. I have to, by a rough estimate, I have to solve the equation out to this sort of, turquoise line that I've drawn here. So again, these are the lowest 100 channels, which means that if I want to go up to 3,000 Kelvin or so, I'm going to need roughly the lowest 100 channels. Well, again, if done correctly, we can handle this. People have handled certainly many more. And just to summarize all of those requirements, we're going to need maybe 100 channels for each angular momentum. We're going to need angular momenta, the little angular momenta, that's the 2-body molecular angular momenta, up to 30 or 40, okay? But we're going to need total angular momentum at least 30 to go to a temperature of 3,000. Incorporate the identical particle symmetry, make sure that we have all the formalities of 3-particle scattering under control, because again, some of these things weren't even written down until we did it within the last several years. And finally, assuming we can get all the scattering part done, we need the quantum chemists to be able to provide good Born-Oppenheimer surfaces for us to work on. Now, it may be, I've assumed that I could work only on the lowest Born-Oppenheimer surface. It could be that I have to actually couple a few Born-Oppenheimer surfaces together, which means I multiply all of these things by however many surfaces I need. Okay? Fortunately for these light systems, things like helium plus hydrogen, there aren't so many electrons, so those surfaces are around. Okay? So I think we can actually handle all of these things. with some of the technical developments we've done lately, and actually be able to solve this in this astrophysically relevant regime. Now, of course, what about the bigger question, the H plus H plus H? Well, it is even more technically challenging than the simple system with helium that I described. That's why we aren't doing it first. I think if we're successful with the helium case, we can do the hydrogen case. But there is one problem, extra problem, that comes up with three identical particles, is this issue with conical intersections. Don't want to talk about the details, but it's it's things like geometric phases, Berry phases, if any of those terms mean anything. If not, it's just complication. Okay, and by the way, symmetrizing three particles also gets a lot more complicated than just symmetrizing two when they're spin 1/2. But again, all known things in principle. There were several other important systems listed in Simon and Daniel's paper, and they've mentioned some in their talks. But if it's a three-body system, we can probably handle treating it, or at least if it can be approximated as a three-body system, we can handle treating it. So the H plus an electron, that could be H plus H minus, that could be any combination of those three things. If it's reasonable to approximate this as a three-body system, we can do something with that. Okay, and I have just listed a few others. This is maybe a little bit bigger question whether we can actually handle that as a three-body system, treating H2 just as a single body that doesn't do anything. But there are many other people who can handle a three-body continuum. So there's not somebody going to be doing a four-body calculation on this anytime soon. So when you're the only game in town, you may as well play. Okay, and I think that is all I have. So my voice lasted this long. Maybe I'll get some more questions. Thanks.